Hi everyone. We'll start with a reminder about when you have a power that has a base with multiple components within it, that the exponent actually applies to each one of the components. So that 4 as an exponent has to apply to all parts of that base. There's two ways we can think about this. We can begin by writing out negative 2x to the power 3 4 times, because the exponent 4 tells us to do that. Or we can write it out so that we apply the 4 to each component. So we apply the 4 to the negative 2 part of the base and to the x to the power of 3 part of the base. You can see as both examples are worked out that you're going to wind up with the same answer either way. Once again, we'll note that the second method is a little bit more efficient. Sometimes you'll come across questions that have exponents within them, but the terms are being added and subtracted. Remember that the exponent laws only apply when doing a power of a power, or when multiplying powers that have the same base, or when dividing powers that have the same base. In our first example, none of these circumstances are present, so we are just going to have to do this question using our regular old BEDMAS format. We'll do 4 to the power of 2 and get 16. We'll subtract 2 to the power of 3, which is 8. And we'll add 3 to the power of 4, which will be 81. And once again, we'll use BEDMAS to simplify and evaluate this. Our second example is very similar. We don't have powers that have the same base that are being multiplied or divided or power of power. So in this case, we are going to use BEDMAS again. The only tricky thing within this example, and it's definitely noteworthy, is this 2 to the power of 0. I'd like you to pause the video and go ahead and try to write any number in your calculator and then raise it up to the power of 0 and see what happens. Pause the video now, check that out, and then press play after you have made your findings. So you probably found that when you raise any base to a power of 0, you're going to get 1. So 2 to the power of 0 will be 1, and we'll subtract from that 3 to the power of 2 and divide that by 2 to the power of 3. So that's going to simplify to 1 minus 9 divided by 8, and that will give us negative 8 divided by 8, which will be negative 1. The remaining examples that I'm going to show you in the video are going to be level 4 examples. So if you feel like you want to do some practice with the skills you've learned up until this point and then come back and view the rest of the video later, please feel free to do that. In these cases, we are looking at expressions that don't have the same base within them. And that's a problem for us because the exponent laws won't apply if they don't have the same bases. However, every once in a while, you're going to get an exponent question where you can manipulate the bases so that you will have a common base and then you can use the exponent laws. For instance, in the first question, we have 2 to the power of 12 times 4 to the power of 8. They don't have the same basis, so we can't use the exponent laws, unless we reconsider the fact that 4 could also be written as 2 to the power of 2. If we do that, then all of the powers have the same bases and we can use the exponent laws. We'll keep the 2 to the power of 12 and we'll multiply that by 2 to the power of 2 all raised to the power of 8. This means we'll be able to multiply that power of a power. So we'll wind up with 2 to the power of 16. Then we can use the exponent laws further to simplify 2 to the power of 12 times 2 to the power of 16 is going to be 2 to the power of 28, because we'll be able to add those exponents because they have the same base. In our second example, you can see that none of the bases are the same again, but they all can be written with a base of 3. 81 can be written as 3 to the power of 4, 9 can be written as 3 to the power of 2, and 27 can be written as 3 to the power of 3. This will allow us to use our exponent laws again. So we will multiply all of those power of powers to get the new exponents. And then in the numerator, we'll be able to add the exponents because the bases are the same. And then following that, we'll be able to use our dividing power law and subtract the exponents. Remember, this will only work if they have the same base. And if you look at a question and they don't have the same base, you can always look at it with the perspective of, could you manipulate any of the bases so that they could be written with the same base across all of the components within the question. One thing that you will notice is if you are working with powers and you find yourself working with really big numbers, if you're expanding things on your calculator and you're working with these numbers that are just really, really big, that might be an indication that you could have used the exponent laws. And so you might want to backtrack and look for opportunities to use the exponent laws rather than work with really big numbers. Here's a couple more examples where we'll need to consider bed mass as we work our way through the questions. In the first example, we're going to have to see that that power of 2 is going to apply to all components within that base. So we're going to need to write a base of 2, and that exponent of 2 will apply to it. And we're going to need to write the other component within the base of the x to the power of 5, also being raised to the power of 2. We can continue, and we'll need to do the same thing with the second term as well. We'll need to raise that negative 3 to the power of 2 and that x within the base to the power of 2 as well. This will allow us to expand where possible or evaluate where possible. So 2 to the power of 2 will be 4, and we can multiply the exponents to get x to the power of 10 here. That's the power of a power law at work. In the next portion, we will do negative 3 raised to the power of 2, which will give us 9, and then we'll have x to the power of 2 as well. At this point, there's nothing more that we can do with this question because these are not like terms. They can't be combined. We'll learn more about collecting like terms when we do our polynomials unit, but for now, what you need to recognize is that we cannot add 4x to the power of 10 with 9x to the power of 2 because they are not like terms. Like terms require the same base and the exponent component of the term to be the same. In our final example, we're going to need to do what's inside the brackets first. So again, we're following bed mass. So we'll begin by multiplying out the coefficient components. So we'll do the negative 8 multiplied by the 6, and we'll get negative 48. Then we'll note that the powers have the same basis, so we'll have m to the power of 3 added with a 4. That whole thing is going to need to be raised up in a future step to the power of 2. So we'll just copy down the denominator for now so that we can continue. Inside the brackets, we can simplify to negative 48 m to the power of 7. Again, that's going to be raised up to the power of 2. And our denominator can stay the same. As we deal with the numerator, we're going to need to once again recognize that that 2 is applying to both components within the brackets. So we're going to need to write out the negative 48 raised to the power of 2 and the m to the power of 7 also raised to the power of 2. Once again, we'll keep the denominator the same for now. There's nothing we can do with it until we've simplified the numerator. As we continue to work this through, we're going to have to do negative 48 squared, or negative 48 times itself. And then we are going to need to do m to the power of 7 raised to the power of 2. That component's going to allow us to multiply those powers. So we're going to have m to the power of 14 in the numerator. In the denominator, we are going to have negative 16 m to the power of 2. Now we can divide. So we'll divide the 2,304 by negative 16, and that will give us negative 144. And then we can subtract the exponents because they have the same base and they're being divided. So we will have m to the power of 12. And we'll leave our answer at that.